You already know what energy is. You've known since you were a child. You felt it in the warmth of sunlight on your skin. You burned through it during a long run, or lost it after a sleepless night. You've said, "I don't have the energy for this," more times than you can count. The word lives in your body, in your language, in your daily experience. It feels like one of the most familiar things in the universe. And that is exactly the problem. Because Richard Feynman, one of the most brilliant minds physics has ever produced, a man who dismantled complexity for sport and turned confusion into clarity as naturally as breathing, sat in front of a camera and said something that most people have never fully heard. He said, "We have no idea what energy is, not in the way you think, not in the way the textbooks taught you." He wasn't being modest. He wasn't performing intellectual humility for an audience. He was making a precise, technical, deeply unsettling statement about the nature of reality itself. What Feynman meant is not what you were told in school, and the gap between those two things, between the comfortable definition and the actual truth, is one of the most important intellectual distances you will ever cross. Stay with that for a moment. The version of energy you were handed goes something like this. Energy is the capacity to do work. A rock perched on a cliff has potential energy. A moving car has kinetic energy. When you eat food, chemical energy converts to thermal energy and mechanical energy. Everything flows, everything converts, and nothing is lost. Clean, elegant, satisfying. That definition is not wrong, but it is profoundly incomplete. In the same way that saying a symphony is organized sound is not wrong, but misses everything that actually matters. The equation E equals mc squared feels like it explains something. Mass times the speed of light squared equals energy. You've seen it on t-shirts. You've nodded at it. But what is the c squared doing there? Why does squaring the speed of light turn matter into energy? What is it that mass and energy actually share that allows them to convert into one another? When you push past the formula into the question beneath it, the ground disappears. Feynman's honest admission wasn't a confession of failure. It was a doorway. He was pointing at something physics knows with extraordinary precision. How energy behaves, see how it transforms, how to calculate it down to the last decimal, while simultaneously acknowledging that what it is remains, in the deepest philosophical sense, unknown. We can measure it perfectly. We cannot define it fundamentally. That is not a paradox for science to solve later. That is the current state of our best understanding. Begin with the first movement of that descent. In classical mechanics, energy is a number, a single abstract quantity assigned to a system. Newton's physics didn't even have the concept fully formed. The idea of energy as a conserved quantity took centuries to crystallize, and it only emerged because mathematicians noticed something strange. Across radically different physical situations, collisions, pendulums, falling objects, a certain numerical relationship kept surviving every transformation. Something was being preserved. They called it energy because they needed a name. But naming is not explaining. The conservation law is extraordinarily real. The reason why anything is conserved at all points towards something stranger. Emmy Noether, in 1915, proved that conservation of energy is not a brute fact about the universe. It is a consequence of something more fundamental. The fact that the laws of physics do not change over time. Energy is conserved because time is symmetrical with respect to physical law. If the laws governing the universe were different yesterday than today, energy would not be conserved. The number we call energy is, in Noether's framework, a shadow cast by time's uniformity. We are not measuring a substance. We are measuring a symmetry. That is not the same thing. Now go deeper. When Einstein collapsed the boundary between mass and energy, he did not discover a recipe for conversion. He revealed that mass and energy are not two different things that can trade places. They are aspects of the same underlying structure. The question, what is energy, became immediately entangled with the question, what is mass? And mass, it turns out, is almost entirely not what you think it is either. The proton in every atom in your body has a mass, but add up the quarks inside it, and their known masses account for only about 1% of the proton's total mass. The other 99% comes from the binding energy of the strong nuclear force, from the frantic motion of those quarks and gluons confined in an impossibly small space. Most of your mass is frozen motion. Most of what makes you solid and real to the touch is energy in a particular configuration, not matter and energy coexisting. Energy taking the form you call matter. The floor beneath your feet is not a surface, it is a field interaction. Your feet do not touch the floor in any meaningful physical sense. The electrons in your body and the electrons in the floor repel each other electromagnetically, and what you interpret as contact is the force of that repulsion. What you call solidity is electromagnetic energy arranged so that it resists compression. Energy is not in the physical world. In a very real sense, energy is the physical world. Go further still. In quantum field theory, the most experimentally verified framework in the history of science, does not describe a universe filled with particles moving through empty space. It describes a universe composed entirely of fields. Matter particles, force carriers, every phenomenon you have ever observed. All of them are excitations in these underlying fields. The electron is not a tiny solid ball. It is a ripple. And what drives that ripple, what sustains it, what allows it to interact with other ripples, is energy. Not energy as a property of the ripple. Energy as the ripple itself. The distinction between substance and property collapses. There is no particle having energy. There is energy organized into what appears to be a particle. Even the vacuum, what we casually call empty space, is not empty. Quantum mechanics requires that space itself seethes with fluctuating energy, and virtual particles popping in and out of existence faster than observation allows. The Casimir effect, measurable in a laboratory with parallel metal plates, demonstrates that this vacuum energy is not theoretical. It exerts real, measurable force. The ground state of the universe contains energy even when it contains nothing else. Energy predates matter. Energy will outlast the last star. At this point, someone will say, "This is all semantics. The word energy is just a label we use to track something." The mathematics works. The predictions are accurate. The bridges stand, the reactors run, the satellites navigate. Why complicate something that functions perfectly well as a practical tool? This is the strongest version of the counterargument, and it deserves a serious answer. Feynman himself was largely a pragmatist. He believed fiercely in the power of calculation, in the priority of prediction over philosophy. But even he drew a line. Because the history of physics is a history of conceptual revolutions that could never have occurred if scientists had been satisfied with tools that worked. Classical mechanics worked until it met black holes and quantum phenomena and broke completely. When your model fails at the edges of reality, the reason it fails traces back to the assumptions you never examined, the words you used without knowing what they meant. If we treat energy as understood because we can calculate it, we close the doors Feynman was trying to open. The question is not whether the mathematics works. The question is whether we are willing to sit with what the mathematics is actually telling us, which is that something profound is happening at the base of reality. Something that our language, including the word energy, is not yet fully equipped to describe. And here is where the vertigo becomes something else entirely. If energy cannot be fully defined, if our most fundamental physical concept is, at bottom, a quantity we know how to measure but not fully explain, then we are beings who have built civilization on something we do not completely understand. Every circuit, every engine, every explosion, every heartbeat runs on a principle that remains, at its core, open, not broken, not wrong. Open. That openness is not a failure of physics. It is physics being honest about what it is. Not a final description of reality, but the most disciplined and rigorous attempt to map something that may always exceed the map. The universe is not obligated to fit human definitions. It is under no contract to be fully knowable. What physics offers is not certainty, it is precision within acknowledged mystery. And that distinction transforms the way you look at everything. You are not a machine running on a fuel. You are a temporary, extraordinarily improbable configuration of something the universe does not fully explain to itself. The energy flowing through you right now has been cycling since before the Earth existed. It does not belong to you. It passes through you. And the fact that it organized itself, for a brief time, into something capable of asking what it is, that is not ordinary. That is the universe achieving a kind of self-awareness it does not guarantee and cannot repeat. If you are still here, Chuan, you are not looking for simple answers. You are looking for better questions, which is the only honest direction curiosity can move. That is what this channel is built for. Not to tell you what to think, but to show you where the edges of thinking are. The Invisible Laws explores the structures underneath what we assume we understand. Because the most important ideas are almost always the ones hiding behind the words we stopped questioning. If that is the kind of mind you want to keep building, you know where to find the next question.